Section 5.6 brought to you by Star Wars Lego Droid Thing. I didn't like these episodes as much. I don't know the name of these things. So 5.6 is the applications, essentially models of exponential and logarithmic functions and kind of how we could see them used in daily life. So let's just dive right in. This is the typical exponential growth model. So we have some initial p-value at time 0. We tend to think exponential growth as growing. This one's like continuous growth, but the connection here is, recall we wrote, boy, I totally forget how we wrote it. Y equals a b to the x. And so our connection between this equation and this equation is that e to the k equals our b, our growth rate. So we could solve for it if we wanted to convert equations in this form back to this form or vice versa. So note here, k is the exponential growth rate and is always positive when we're talking about exponential growth. When we're talking about exponential decay, that k would have to be negative. So we start with a sample here of bacteria culture. It contains 50 E. coli cells. So there's our P naught. And then the exponential growth rate under optimal conditions is about 4% per minute. Get ready, that's wild. So our K here is this as a decimal. And a lot of times we turn T like into years and months and hours. It's just whatever you set T to be, as long as you acknowledge that. So if we presume optimal growth, how many bacteria will there be in 1 hour? Well, if T is in minutes, then we could just write this equation as the amount of E. coli present, P of T, is equal to this initial value of 50 times e to our growth rate, and then an hour, 1 hour equals 60 minutes. So we would have to put in a 60 here and then evaluate that. Whatever that comes out to be is the population value at this point. So I'm just going to smash this in my calculator so I don't have to switch screens. I'm getting this to be approximately 551.18 E. coli cells. So then we're saying, well, how about after 3 hours? Well, now we just have to recognize how many minutes is 3 hours. So if 1 hour was 60, 3 hours would be 3 times 60, which is 180 minutes. Same equation. By the way, technically right here, I should have put P of 60. So down here, I'm going to put P of 180 equals same initial value of 50. Now raised to the 180 power, and let's see, what does our population look like here? Oh boy, I messed that up. 0.04 times 180. It is now at 66,971.54. I'm just going to say cents at this point. Now, clearly, there's going to become a time that this idea of optimal conditions doesn't work anymore. E. coli takes like what material, like food to grow. So eventually that's going to run out. If you think about your microbiology classes, your petri dish can only support so much. So there's going to be an upper limit on this. This last question is a nice connection back to section 5.5. This says how long, in other words, for what T value will it take for there to be 1 million bacteria? This 1 million is now our P of T, and everything else is the same. So we're just going to plug this in and solve. So we'll have 1 million bacteria equals our initial 50 at a growth rate of 4% per minute, and put a T, and now we have an exponential equation to solve. We solve it using logarithms. If you recall, we wanted the exponential piece by itself, so a coefficient of 1. So divide both sides by 50. It feels like 1 million divided by 50 becomes 20,000. So this is 20,000 equals e to the 0.04 times t. And at this point, we pick a logarithm. We pick any base we want. Since this exponential is base e, I would encourage you to choose natural log, because then the right side just becomes 0.04t, and the left side is whatever natural log of 20 is equal to, or 20,000, excuse me. We then divide both sides by 0.04, and our solution is natural log of 20,000 divided by 0.04. If we were in class, I would tell you how I prefer exact values until it comes to application problems, because when's the last time you told someone that, yeah, it took me a natural log of 20,000 divided by 0.04 minutes to drive to work? It's just not something we would ever say. So you type that in your calculator, get the approximation to kind of make sense of the amount of minutes it would take for you to grow 1,000,000 bacteria under optimal conditions. My calculator tells me 247.59 minutes. A lot of people don't talk in that language either. They would say, oh, that's 4.126 hours. And if you're wondering how I did that, I just divided this amount by 60 to get the amount of hours. Either one of these is correct.